Well, let's get started here. Welcome back from the Thanksgiving break for everybody. Um, you remember that before the break, I got started talking about the elasticity of nematic order. That is to say, if you have a nematic liquid crystal and the director is oriented in different directions in different places, something like this, for example, okay, then there is some extra energy associated with the variation compared with what would happen if the director were the same everywhere. Okay? This extra free energy associated with the variation is the elastic free energy. That is, it is the free energy associated with having gradients of n that are not equal to 0 compared with what the free energy would be if the gradients were all equal to 0. So in the time just before the break, I showed you the simplest version of the elastic free energy. Okay? And in the simplest version, we would say the free energy is an integral over the entire volume of the liquid crystal. And the free energy density is some 1/2 of an elastic constant times the sum of all the possible derivatives of the director squared. Right? So you recognize this kind of tensor notation, right? That this expression is a sum over all values of the index I and all values of the index J. All right, so what this means is dx and x squared plus dy and x squared plus dz and x squared plus dx and y squared plus etc. Right? There are 9 terms that are getting added up, and they all contribute. And they all contribute with the same coefficient, right? That there's this coefficient up in front, what we could call an elastic coefficient, which shows how much free energy is associated with variations in the director. Okay? And so if you have some certain derivatives, right? So if the director is rotating by so many degrees per centimeter, right, then you get a set of derivatives over here. And this says that all these derivatives, you square them and add them up. And that gives you the elastic free energy. That is the simplest version of the elastic free energy for a nematic liquid crystal. It is a good starting point, but it is not a good ending point. Right? This is not sufficient for designing most kinds of liquid crystal devices. The reason why it is not good enough is that it has the same energy cost for all possible variations in the nematic director. Okay? But in fact, different kinds of variations might have different elastic constants. They might have different energy costs. So for example, here is one picture of one possible arrangement of the director field. Okay, let's draw another possibility. Another possibility would look like this. Okay, so in this possibility compared with, whoops, I meant to just highlight. In this possibility compared with this possibility, there's the same variation in terms of how many degrees per centimeter. So I claim that if you were to take all these derivatives and square them and add them up, you get the same thing for this picture or for that picture. Right? But you can see these are two different physical situations. They're not the same physical situation, right? That the relative orientation of the gradient versus the director itself is different in these two cases. In this case, on the right, as you go along in the director orientation, you get some variation. Right? In this case on the left, the variation is, well, it's mostly perpendicular to the average director. So there's no reason why those two things have to have the same energy cost. Right? And so we need an improved version of the elastic free energy, which recognizes that those kinds of variations can have different energy costs. Okay. So let me present my version of how we would break up those things. Okay. So what we want to do is say we need different elastic constants for the different types of variation. And so we could say, for just I give you a few vocabulary words, we could, for different distortions in the director, or different deformations, or different gradients, or different elastic modes. These are vocabulary words that you might see that people could use in this kind of a situation. Okay, so what we really want to do is to identify what are the different kinds of elastic modes, and then say, let's make up different elastic constants, one for each of them. Now, this is a situation where I have a way of setting up the calculation that's a little bit different from the standard way. I really like my way. I'm going to show you my way, and then I'm going to show you how this is equivalent to the standard way. Okay. My way, by the way, is not in the textbook, because I came up with it more recently than the textbook. But instead, there is an article that I published in Liquid Crystals Reviews in 2018. And so that article is posted on the Blackboard site for this class. And so what I'm presenting in this class is a short version of the story that's in that article. Okay, so the story in this article is based on the idea of tensors, right? We want to break up the tensor del I and j. Okay, so this is a tensor. It's a 3x3 matrix, right, which shows all the ways that one component of n could depend on one component of position. Right? And so this is a 3x3 array of all of the possible derivatives. Okay? And I want to break up this tensor, or the mathematical word would be decompose this tensor into the fundamental elastic modes. Right? And the way that I do it, which is justified in that article, is like this. Okay, I have a construction that this set of derivatives can be written as the sum of 4 types of modes. So let me write this out and then I'll explain all of the pieces. Plus 1/2 s ij minus ni nj. Okay, so this is a construction which is breaking the tensor over here into one part, which is described by a vector, a bend vector, one part which is described by t, one part described by s, and one part described by this tensor. Okay, now let me explain to you each of these 4 pieces. Okay, the equation is saying that there are fundamentally 4 pieces of this kind of director deformation, okay, which are 4 types of mathematical objects. The first of those pieces is what's called bend. So this is a director deformation which looks like either of these pictures over here. Okay? So this is a director deformation where as you go along the director, so if you go along this direction, you see a variation in which way the director is pointing. Okay. That is to say, if n is mostly in the z direction, whoops, if n is mostly in the z direction, then we could look at how does nx depend on z, and how does ny depend on z. Okay. So that's what these 2 pictures over here show. Nx is a function of z there, and y is a function of z there. Okay. In general, if n is in any arbitrary direction, then the bend is described by this combination. That is, you take n cross the curl of n. Okay? So the curl of n is a pseudo vector. And then n is a proper vector, so n cross a pseudo vector makes a proper vector. Okay, so this B is a proper vector, and it is in the plane perpendicular to the local n. It has to be perpendicular to the local n because it's an n cross something, and a cross product is perpendicular to the things in the cross product. So it's a vector in a plane. So it has two components. One component is the what's illustrated in this picture, and here's the other component. Okay, so if you have nx as a function of z and ny as a function of z, so that's a vector in the xy plane. So this is one way that a director can vary as a function of position. It has some energy cost. Okay? And the energy cost for this kind of variation is the same as the energy cost for that kind of variation, because there's a symmetry between them. The director could be going like this or like that. And those two things cost the same amount of free energy because you can get from one to the other by just rotating about the n axis. Are you good so far? Any questions already? Okay, I'll go on then. The second mode is called twist. Okay? And so that is the mode that comes in here. And an illustration of twist is right here in this picture. So in this mode, you have the director, which is mostly in the z direction. Well, it's mostly in some direction. Okay, so we'll say if n is mostly in the z direction, then we can look at the combination dn y dx minus dnx dy. This combination of derivatives represents a variation like this one, where the director is sticking up in the middle, and it tips over in one direction as a function of x, and it tips over in the perpendicular direction as a function of y. Right, so you can see my pencil rotating as I move to or from the camera. Okay. So this is called twist, right? And people sometimes also call it double twist because it is a variation both as a function of x and as a function of y, right? It's varying like this as a function of x and also as a function of y. So right at the center, the director is vertical. And then when you go out, it's cutting around like a cone. And then when you go farther out, it's like a cone that's tipped over more. The type of object, or this object, it has this mathematical expression if n is mostly in the z direction. If n is in any old direction, then we get this mathematical expression. That is to say, we take the curl of n, that's a pseudo vector, dotted with n. That's a proper vector. So the dot product of these two things is a pseudo scalar. So it's a pseudo scalar that tells us how much of the right-handed twist do we have versus how much of the left-handed twist do we have. Okay, that's the second mode. The third mode is what's called splay. That is the piece that's written out here. Right? What it looks like is this little cartoon. Okay, so this is a situation where the director is tipping outwards as you go away from the central axis. Okay? So if I go out in the x-axis, the director tips over in x. If I go out in the y-axis, the director tips over in y. So we could say, if the director is mostly in the z direction, then this deformation is represented by the combination dnx dx plus dny dy. So it shows how much is the director going outwards in x as a function of x, plus how much is it going outwards in y as a function of y. If the director is in any arbitrary direction, then the expression just looks like that. Okay? Then the expression for splay is just the divergence of n. So this type of mathematical object is just a proper scalar. It's proper because it doesn't have any Levi-Civita symbol or any right-hand rule in it. It's a scalar. It's just a single number which stays the same if you rotate everything about the vertical axis. This thing is called splay. I personally would equally be happy to call it double splay because it is a director that's varying as a function of x and as a function of y. Double splay is just my own personal word. It's not a standard word in the liquid crystal literature. Now, there's a fourth mode. The fourth mode does not have a standard name. The fourth mode is not talked about a lot in the liquid crystal literature, but I'm arguing that it is also important. Okay? It does not have a standard name. It was first discussed in a very mathematical article by these researchers in the United Kingdom, Nashan and Alexander, who came up with a very mathematical sounding word for it. They called it anisotropic orthogonal gradients of n. I wrote about it in this Liquid Crystal Reviews article, and I said, what? That phrase is way too long. I can't use that phrase. So I made up another word for it. I called it biaxial splay. And, but mostly I just call it by the symbol that Michon and Alexander used, which is this delta ij tensor. So what is this mode? Okay. What it is easiest to see if we imagine that the director is mostly in the z-axis. Okay. So if n is mostly in the z direction, then there could be a mode where the director tips outwards in one direction and inwards in the opposite direction, in the perpendicular direction. Right? So that's what's shown in this picture right here. Okay, so in this picture, we have a director which is tipping outwards as a function of x, right? Right in the middle, it's in the z direction. As a function of x, it's tipping outwards. But as a function of y, it's tipping inwards. Right? A director could totally do this. This is certainly a possible deformation mode. And it's not any of the other things that I described to you so far. It's not bend or twist or splay. It's a fourth sort of thing. It should be on the list of possible modes. So it could be described mathematically by a difference, the derivative of nx with respect to x minus the derivative of ny with respect to y. Okay? That shows how it goes outwards in x and inwards in y. Now, what if you rotate by 45 degrees? Okay, so if you take everything and rotate by 45 degrees about the vertical axis, then instead of this picture, you get to this picture. Here, the director is vertical in the middle. If you go out along one of the diagonals, it tips outwards. And if you go along the other diagonal, it tips inwards. Right? So this is described then by the derivative of nx with respect to y plus the derivative of ny with respect to x. These things are two components of a tensor. And indeed, we can work out mathematical properties of the tensor. The tensor is written out here in general. Okay? And what I show in that article is that this is a symmetric traceless tensor in the plane perpendicular to the local n. Okay. So if the local n is mostly in the z direction, then this is the xx component of a tensor, which is equal to negative of the y component of a tensor. Whereas this thing is equal to the xy component of the tensor, which is the same as the yx component of the tensor. So this is a fourth liquid crystal mode, which doesn't get talked about very much, but it is a possibility. It is on the list of possible modes for the liquid crystal. So here I have a list of 4 modes, right? Display, bend, twist, and this delta. Okay, now each of these modes has to cost some elastic free energy. So we could say that the elastic free energy of a liquid crystal must be an integral over the volume of something times space squared plus something times twist squared plus something times the bend vector squared plus something times delta squared. Now, delta is a tensor. What does it mean to have delta squared? Well, we could say the trace of the tensor squared, like that. So this thing, the trace of the tensor squared, means delta ij delta ji, which is equal to delta ij delta ij, because it's symmetric. This is to say, each of these kinds of derivatives can contribute something to the elastic free energy, but they don't have to contribute the same amount. They could all contribute each a different amount. Okay? And so these blanks, which I'm going to fill in a few minutes, these blanks represent some coefficients that go there, which show what are the energy costs for each of these kinds of deformations. Now, let's compare that with the simplest version. Right? In the simplest version, the free energy is an integral of 1/2 k, a single constant, times this combination of derivatives. One thing that I show in this liquid crystals review article is that this combination of derivatives breaks down to be 1/2 s squared plus 1/2 twist squared plus bend squared plus the trace of delta squared. This is not obvious, but this is something that I show in this article, and you can check. Okay, so that means that the simplest version of the free energy is this 1/4 k times s squared plus 1/4 k times twist squared plus 1/2 k times bend squared plus 1/2 K times the trace of delta squared. So the simplest version of the free energy corresponds to assuming that the numbers that go in these blanks are in the ratio of, a half to a half, a half to a half to 1 to 1. Right? So if we have those special ratios, then the simplest version of the elastic free energy is correct. But in general, they don't have to be those ratios. They could be anything. And then we get the general form of the elastic free energy, which is written out up here. Now, this is my form of the elastic free energy, which I personally love, but it's not what you're going to see from other professors. So let me show you what you're going to see from other professors in other articles. Okay, so that is what I'll call the standard form of the Frank free energy, which people also sometimes call the Frank-Osane or Osane-Frank free energy. The standard form looks like this. It is an integral over volume of 1/2 K11 times splice squared plus 1/2 K22 times twist squared plus 1/2 K33 times bend squared minus a complicated looking thing, which is K24 times the divergence of n del dot n plus n cross del cross n. Okay, so this is what you'll see in articles and other classes. Okay. It's different from what I just showed you in a couple of ways. Right? One way that it's different is that there's no delta in it, right? That mode is just missing. Okay. Another way it's different is that it has this complicated looking thing there. And this complicated looking thing is what people call saddle splay. You might ask, how is this thing related to what I just showed you? Okay. The answer to that is something else that I work out in this liquid crystals review article. This messy looking term, the saddle splay term, is equal to 1/2 splay squared plus 1/2 twist squared minus the trace of delta squared. This is another thing that's not obvious, but it is just mathematically true. And you can work it out just by, it's a whole exercise in working with the kinds of tensor manipulations that I've shown you. Okay, now suppose we put that equation into this free energy. In that case, what do we get? We get that the free energy is this integral of 1/2 K11 space squared plus 1/2 K22 twist squared plus 1/2 K33 bend squared minus K24 times this combination of things. Space squared plus 1/2 twist squared minus the trace of delta squared. Now, let's multiply out and collect up the terms. Okay? This looks like an integral of this combination, 1/2 K11 minus K24 times space squared, plus 1/2 K22 minus K24 times twist squared, plus 1/2 K33 times bend squared, plus K24 times the trace of delta squared. This thing now looks just like the equation that I showed you up here, with certain things that go in the 4 blanks. Okay, so the things that go in the blanks, these are the coefficients of splice squared, twist squared, bend squared, and the trace of delta squared. Okay. So these are the energy costs for each of those 4 elastic modes. Okay, now this thing in blue up here is what you will see from all the other professors you interact with. Okay, this thing that is written out down here, this is the expression that I came up with. Okay, and it's an expression that I love because it looks like the sum of squares of things, right? It looks like there are 4 elastic modes and each of them costs some amount of free energy. And that's what an elastic free energy normally looks like. Okay, so that's why I love this expression. Okay, now you might ask, why do other people use this expression? Well, there are 2 reasons I can say. Reason number 1, because they don't know about my thing yet. But once they learn about my thing, they're going to love it the same as I do. And then everyone will use my thing. Maybe. Okay. Reason number 2. There is an interesting thing which is based on vector calculus. Okay. Let me remind you about a theorem of vector calculus which you may have learned in a multivariable calculus course. Okay. This thing is called the divergence theorem. The divergence theorem says, suppose you have any vector field, let's call it V as a function of position. The theorem states that the integral over a volume, the volume integral of the divergence of the vector field is equal to the integral over the surface of that volume, and that is an area integral of the vector field dotted into the normal vector. This is capital N is the unit outward pointing normal vector perpendicular to the surface. This is a theorem which you might remember from a multivariable calculus course. Usually it comes pretty near the end of the course when people are tired and they might not pay attention to it, but I bet it was covered if you go back to look at your notes from such a course. Okay. The reason why that is important is because this kind of form, the integral over a volume of the divergence of something, that's just like this saddle splay term, right? This is also the integral over a volume of the divergence of something, right? So let's apply the divergence theorem to that integral. It tells us then that the free energy will be the integral over a volume of 1/2 k11 splay squared plus 1/2 k22 twist squared plus 1/2 k33 bend squared. Okay, that's the volume integral. And then minus k24 times a surface integral. Right, the first thing is a volume. A surface integral of n times this del dot n plus n cross del cross n. All of this dotted into the unit outward pointing normal vector. Okay, so in that case, you have a free energy, which is the combination of this volume integral and this surface integral. Okay. Now, in many experiments, maybe even in most experiments, the n is fixed at the boundary. The word for that will be strong anchoring. In many experiments, n is strongly anchored to a specific orientation everywhere on the boundary. It's only free to vary in the interior of the liquid crystal cell. In that case, the surface integral is fixed. It is a constant. It's determined by whatever is happening at the boundary, and it is not free to change. And in that case, the elastic free energy becomes an integral of 1/2 this k11 splay squared plus 1/2 K22 times twist squared plus 1/2 K33 times bend squared plus a constant. And you know that constants don't matter in a free energy. Additive constants don't matter in a free energy because we're always trying to minimize a free energy. And if you're minimizing this stuff, or you're minimizing this stuff plus a constant, you get the same director field either way. Okay. So in those situations where this term becomes a constant, you can say, forget about it. It doesn't matter. It doesn't matter. So, indeed, I would say most liquid crystal scientists have already forgotten about it. Okay, and if you poll liquid crystal scientists and ask them what is the Frank free energy, 99 out of 100 will tell you this thing. And if you say, well, what about the saddle splay part, this part? Then they'll say, oh yeah, I remember I had a class about that once, but I never really understood it. So I'll just forget about it. And so, well, at this point, you can join the 99% if you choose, right? And but I at least wanted to give you this perspective about what happens to these other deformations, right? And that there are, in fact, the 4 modes. There's the splay, twist, bend, and the delta mode, which goes into saddle splay. And it is occasionally important in certain liquid crystal problems where there is not such strong anchoring on the surfaces, but not in the majority of problems. Okay, that is my story about how you get to an elastic free energy. Okay, I have one more brief remark, and then I'll stop for today. Okay, the extra brief remark that I wanted to make is related to splay and twist. You remember I described the twist deformation to you as a double twist. That is, the director field is varying as a function of 2 coordinates. Right? So the director is twisting, going outwards from a central core in both directions going outwards. Likewise, splay is a double splay. That is, the director is going outwards in both directions from a central core. Now, you can also sometimes, not just sometimes, often see a different kind of twist where the director is only varying as a function of 1 coordinate. Okay? That's what's shown in this picture right there. This kind of deformation has a director that depends only on z. It's independent of x and y. So the director is just changing like a screw going up as a function of z. And it's constant with respect to x and constant with respect to y. This might be called single twist. It might be described by an equation like this one. So you might ask, what's the difference between that and the double twist that I showed you before? The answer is, if I put this director into my equations for splay, twist, bend, and delta, I see that it has 0 splay, 0 bend, non-zero twist, and non-zero delta. So this thing is not pure twist, but it's a combination of pure twist and delta. So pure twist is the double twist, but then this thing also has some delta thrown in. So if we want to know what's the free energy of this kind of thing, the free energy for the twist part is like this: a half K22 minus K24 times the wave vector Q squared. The free energy associated with the delta part is a half K24 times the Q squared. So the total free energy is this plus this. So the K24 just perfectly cancels out, and we get something which involves just K22. And so people would say then that K22 by itself is the elastic constant for single twist, even though K22 minus K24 is the elastic constant for double twist. And the same is true for splay, right? That this is a picture of planar splay, right? This is like slices of pizza, right? If you slice pizza, you have splay in the XY plane, but nothing depends on Z. So this is a single splay, right? That the director is just splaying as a function of one coordinate. This likewise is a combination. It's a combination of pure double splay and this delta mode. So the pure double splay has an elastic constant of K11 minus K24. The delta mode has an elastic constant of K24. When you combine them, you get an elastic constant of just K11. And so this reduces to the story that all the other professors will tell you about single splay with an elastic constant of K11. Okay, I am going to stop talking here, and I will have an example of a calculation then to show you on Wednesday. But first, are there any questions about this material so far?
I have a simple question about the sign of those elastic constants. Is K22 always positive, or it can be negative? I'm asking about the sign of all the elastic constants.
Of all four of these elastic constants. That's an excellent question. And I've thought a lot about that. In normal liquid crystals, these things should all be positive, right? Meaning that the lowest energy state is one which is just uniform, that has no derivatives of n, right? And any derivatives of n cost elastic free energy.
Right.
And so these constants should all be positive, and in fact, if you look at expression like this one, right, it's not just that K22 should be positive, but the difference K22 minus K24 should be positive, right? So K22 should be greater than K24.
Right.
And likewise, K11 should be greater than K24.
Mm-hmm.
This is a classic result in liquid crystal physics, that these things should be positive, and that's called the Ericsson inequalities.
Mm-hmm.
And so Ericsson figured it out a long time ago with a different sort of argument. And here, I think that this expression for the free energy provides a nice way of seeing why the Ericsson inequalities should be true.
Mm-hmm.
Now, are they really true? That can be kind of a subtle point. There are certain liquid crystals which seem to have an instability to the formation of double twist. This is a family of liquid crystals which are studied in the laboratory of Professor Lavrentovich, okay? And these are what are called lyotropic chromonic liquid crystals. And there are a bunch of experiments in Professor Lavrentovich's group and at other universities, which seem to show that these materials tend to make a twist. That is, they can go into a twisted configuration even though they are not chiral. Okay, so I should say they are not chiral, but there are some experiments in which they form a twist, which can be either right or left-handed. So that would show up in experiments where people put the liquid crystals into a small cylinder. Right? So if you have some narrow cylinder like this, you might expect to see the director field just along the axis of the cylinder everywhere. But instead, it tends to form something that's winding around the cylinder. And it can either wind around in a right-handed way or in a left-handed way, like that. And so maybe this could be a situation where not K11, excuse me, K22 minus K24 is negative. And so this could be a material which violates the Ericsson inequality in that way. So I'd say this is sort of a current research question. The normal situation is to have all those coefficients positive, but there could be an unusual situation like this where that's not the case.